Alright, this time we're going to talk about the Buckingham pi theorem, which is used in dimensional analysis. So, first things first, one can use the Buckingham pi theorem. Well, Frank White basically sums up here. He says that you need a proper relationship between variables in a physical process, and you need dimensional homogeneity. So, every single equation that we've been dealing with up till now has had dimensional homogeneity. What that means is just that it was what we were talking about before. When you're adding terms, the dimensions need to be the same because you can't add apples and oranges together. If you're going to add things together, they need to have the same units. So equations from physics obey this principle, and that's what we're going to be worrying about, so we don't have to worry so much about this condition. So what about the actual Buckingham pi theorem? Well, he says quite a bit on it. So this is part one of the Buckingham pi theorem, and this is part two of the Buckingham pi theorem. So if you want to check this out, you could pause the video now and read them, but I find that it's much easier to understand what's really going on just by doing examples. This PDH here simply refers to this. So this is the principle of dimensional homogeneity. Alright, so let's get started by working this example here. So we're told that we have some dp dx, and there's a bunch of variables in the tube, and we want to formulate it so that we could write dp dx as a function of these three other variables, mu, u sub m, and r. So in the Buckingham pi theorem, the first thing we need to do, well, first I should state the problem we're doing. So we want to find a function for dp dx in terms of the other variables. So the first thing we want to do is we want to note how many variables that we have. And in this case, since there's three variables over here and one over here, we have a total of 4 variables overall. Okay. The next thing we need to do is we need to write out the dimensions of each of the variables that we see here. So some of them are pretty easy. If you look in the problem, the radius r, that's just going to be a length. So we're going to call lengths L. As for this u sub n, that's going to be a mean velocity. So again, that's not too bad. So we know the velocity is in meters per second, so that's in length divided by time. I'm putting the time up in the numerator for reasons you'll see later, but know that t here stands for the dimension time. Lastly, we have, well, second to lastly, we have this viscosity, function of the viscosity mu prime, and if you've worked with viscosity before, you know that the units of viscosity look like this. Again, if you don't know that those are the units of viscosity, don't freak out too much, it's not that important. And lastly, this dp dx is a little tricky to figure out, so let's break it into pieces. We know that it's the derivative of pressure with regards to position, so we know that we're going to have, since we could approximate this as delta x in the denominator, we could say that we have this length unit over here. We know that pressure is force per area, so we could basically put in these terms, and then since you know that force is in newtons and you know that F equals ma, you could work through that and slowly get everything into units dealing with m for mass, L for length, and T for time. So I'm just going to get rid of everything in between, and we know that dp dx could be represented in this way. So the next thing you do when you're using the Buckingham pi theorem is you look over here on the left and you say, how many different dimensions do I have? Well, we have m, we have L, and we have T. So from that, we could conclude that our J variable, which I'll get into in a little bit, is going to be, well, less than or equal to 3. So we'll talk a little bit more about why this is less than or equal to in a little bit, but know that J is less than or equal to the number of unique dimensions in your problem, and here we have M, L, and T, so we have 3. The next thing we know is the theorem states that the number of pi groups that we're going to get is going to be equal to n minus j. So I'll write that over here. N minus j equals the number of pi groups we have, and here we know that n equals 4 and j equals 3, so there's only one possible pi group that we could form, and we'll talk a little bit about what those pi groups are in a little bit as well. Just know that a pi group is essentially a dimensionless group, so that's what we're looking for when we're doing this analysis. We're trying to find dimensionless groups. So the next thing you do is you say, okay, these are the four variables, r, u, mu, and dp dx. I need to have 3 of these in what I call a repeating grouping. Now, since I'm interested in dp dx, I'm going to choose r, u sub m, and mu as my repeated grouping. And again, this won't make much sense right now, but you'll see once we start doing more problems. We're going to do a lot of problems today. So you write your pi group, your dimensionless group, as a function of the variable you're interested in. So that's the one here. This guy will change when we do some problems later. But over here, this is your this is your grouping. So these are your repeating vars. So whenever you're forming different pi groups, you're going to be using these guys in a power law relation. So that means you have exponents a, b, and c up here that you do not know yet. Now you know that this pi group needs to be dimensionally homogeneous. So what we're going to do is we're going to take the dimensional representation of each of these variables, and we're going to plug them in here and see what the algebra looks like for that. And it will look like this. So don't get confused as to where these came from. These are simply the dimensional representations we came up with over here when we were listing the dimensions of each of these variables that we were interested in. Okay, and why is this 0? Because remember, a pi group is dimensionless. So it doesn't have any dimensions, so its dimension is 0. Okay, so how do we find A, B, and C that solve this problem? Well, look and you'll see that all these variables are being multiplied by each other. So when we're solving systems like this, it's actually going to be like you could break it into 3 separate products. You could break it into m terms, you could break it into l terms, and you could break it into t terms. And each of those, they're exponents, because we're multiplying everything. Those exponents must add up to 0. So what do I mean by that? Well, they're going to look something like this, and there's going to be a lot of things going on, so don't get too freaked out. So, okay, let me explain this bit by bit. So if we're looking just at m, we could write a series of equations. Well, we could write one equation for m. So that comes from just the exponents of each of the terms that have m. So over here you see that there's one m and it's being raised to the a power. So we know that there's 1a1. Over here there's no m, and over here there's no m, so those are going to be zeros. We see a m over here, so we add that as a plus 1. So if you didn't break this into addition of the exponents, it would look like m times m to the a equals 0. Okay? Well, okay, we should be a little bit careful here. This shouldn't be equal to 0. We know that the exponents need to be equal to 0. So I guess technically this should be a 1. I'll correct that later if I'm wrong. I'll check it out. But you want the exponents to be equal to 0. Yeah, okay, so that makes sense, because the dimension here, since it's dimensionless, it should just be equal to unity. Okay, anyway, we now have a system of linear equations, and notice that these equations are going to be linearly independent. That's an important fact that shouldn't be glossed over. We'll talk about it more as we go through more and more examples. So if you've done linear algebra, you could actually write this system as a matrix, and that matrix is going to look like this. So this is an augmented matrix. That just means that this column corresponds to A1, this column corresponds to B1, this column corresponds to C1, and over this dotted line we have everything on the other side of the equals sign. So we're going to move all three of these constants over here, and we're going to get their opposites, so -1, 2, and 2. And you could use Gauss-Jordan elimination to solve this system, or if you're afraid of that, you could simply use substitution and back substitution over here and solve the system however you want. The result when you solve the system looks like this. So remember, what do these constants represent? They represent the exponents that we found up here in our original equation for the pi group, which is given here. So once we have these exponents, we could simply write our pi group out like this. Okay, and remember, the pi group in itself is just a constant. So if we say that it's a constant k, then we could do this. What this means is that we've found a representation that we have a relationship between dp dx and the other variables in the system times a constant. Now notice again that this is, well, this grouping over here is dimensionless. So that was the entire point of the problem, is that we need to find a grouping of these other variables that, when you combine it with this, becomes dimensionless. And that's our dimensional analysis. Okay, so let's get into, this is one of the simpler problems, so let's get into the nuances of the Buckingham pi theorem. So here we have yet another problem, and here our goal is, once again, is always going to be, you have some variable, try to write it as a function of the other variables. And this chart's just here to help you out with the units, decomposing everything into M, L, T, and this theta over here. And theta is for temperature, it's not for degrees. That'll come up later, so don't forget it. Okay, so again, we're given a shear force or a shear stress that we want to represent as a bunch of different variables, all listed there. So that's going to look like this. We have, in the problem, we're given rho, mu, del, dp dx, velocity, and density. So we want to find an expression for the shear stress as a function of all the other variables. And notice this time, once again, the first thing we do in the pi theorem is we list the number of variables we have. And here it's 6. The 5 here and the 1 over here. Okay. The next thing we do is, for each of the variables that we have in our problem, we're going to list out the dimensions, the fundamental dimensions that they have. So these all come straight from the table here, no real magic going on. So once again, since we have 3 unique dimensions, m, l, and t, we know that our j is going to be equal to 3 or less than 3. Again, we'll talk about when j is less than the number of unique dimensions, but for now, we're going to assume that j is equal to the number of dimensions that we're given. Okay, now remember, how many pi groups are we going to get? Well, we're going to get n minus j gives us the number of pi groups. Here we know we have 6 variables, and we have 3 unique dimensions, so we suspect that we're going to get 3 different pi groups. And remember, okay, well, what we really want to do in this problem is this. We want a pi group that has the shear stress, and we want to write it as a function of 2 other pi groups. And remember, each of these pi groups is going to be dimensionless. So the next thing we need to do is we need to choose our repeated grouping. And our repeated grouping is going to have 3 guys, or it's always going to have the j number of guys. So how do you choose your repeated grouping? Well, your repeated grouping must not form a pi group among itself. Now, since this is a simple problem again, we've actually been told what to use for our pi group. So we're going to use rho u, and we're going to use del. So we're going to use rho u and del in our repeating group. Now, how do you tell that these guys don't form a pi group in and of themselves? Well, remember, the vector space you're working over is going to be in that exponent, so the adding and subtracting of exponents. So we'll actually talk about this in the next problem. I'm just going to try to get you more and more used to solving these in a straightforward manner right now. So don't worry about it yet. Just know that they've given you your repeated grouping, so what you want to do is you want to write the other variables in terms of your repeated grouping. So the other variables are your shear stress, which is your variable of interest, your mu prime, and your dp dx. So when you're trying to get a pi group for your shear stress, you're going to do the same thing we were doing last time. You're going to say pi sub 1 equals the variable that you're interested in, and then your repeated grouping raised to these exponents. And then once again, you're going to set up a system of equations by first substituting your dimensional representation into here, and you should get something like this. And then once again, I'm going to fast forward through most of the algebra since that's not very interesting. You're going to write a matrix and solve that matrix for the exponents. In this case, that's -1, -2, and 0. And then you're going to apply those exponents directly up here to get the final representation of your pi group. And in this case, the one for shear stress, that's going to look like this. Now remember, since our n minus j gave us 3 pi groups, we're going to repeat the procedure for mu prime and dp dx. So you're going to do this line again, but you're going to change this here. And you're going to substitute the other 2 variables into there. And you're going to go through this procedure again, get the exponents, and that'll get you your pi groups. I'm not going to beat you over the head with that, so I'm just going to tell you what you finally get in the end. And that's going to be these 2 groups here. So again, your variable out front, that was not part of your repeating group, times your repeating group to some different exponents. So if you go through the algebra, you should get these numbers, 0, 1, and 0, and 1, 1, and 2. And I'll let you work through that algebra on your own. It's not too important. Now remember, what does the Buckingham pi theorem states? It says that you could take this and you could say, my pi group that depends on the variable I'm interested in can be written as a function of the other 2 pi groups. And remember, those pi groups are dimensionless. So all it's saying is that you could take your pi group that has the shear stress in it and say that is going to be a function of this and this, which are the pi groups of the other 2 variables. Okay, let's get into when things get less than perfect. So this time, again, the problem is pretty much going to start out the same every single way. You have some sort of variable that you want to write as a function of the other variables. So this you should be used to already from the last 2 examples. What we essentially want is we want a function for this variable del in terms of these guys. And again, you count the number of variables you have. It's going to be 4 over here and 1 over here. The next thing you do is you write out the dimensional representation of each of these variables. And that's given here. Again, this isn't too important. You're just going to look up these in a chart like this and get their dimensions. Try not to freak out too much about that. Okay, and here, once again, you see that Give me a sec. You're going to say, okay, I have 3 dimensions. I have L, I have T, and I have M. And you're going to say, since I have that many dimensions, J must be 3. Well, this is the first time that things sort of fall flat on their face. Sorry, I'm sort of speeding through these. Okay, so why does this not work? Why does J equal 3 not work? Okay, well, the thing is, we need an ordering of 3. So we need to make a group of 3 guys, and we weren't told what group we should use. I should also say that we have del. That's sort of important. So we have del over here. Del equals L. Okay, but del's the guy that we're interested in. So let's look at just these 3 over here. We need a combination or a grouping of 3 of these guys, and these are the possible combinations. And you'll see that if you throw del in the mix, you're going to have problems for the same reason. Now remember, these 3 that we're using in the grouping cannot form a pi group among themselves. So how do we know if something forms a pi group among itself? Well, in the vector space that we're worried about, this is going to be the condition. So remember, we're working with these exponents. So you can make a pi group within your grouping if this condition is satisfied. And I'll try to explain what that means. So if one of your guys could be expressed as the product with the exponents of the other 2 guys. Okay, what does that mean? Well, take a look over here. If you use P, L, and I, we know that if we take I, we could say that it's simply going to be P to the 0, so we're going to basically ignore this guy, and we're going to say it's going to be L to the 4th. So we've written I as a combination of the other 2 guys in its grouping. So we know that that's not going to work, because that forms a pi group. We also know that the same problem is going to be in LIE, because we know that it has I and it has L. So we could again say that I is a combination of L and E to the 0. What about this last group, P, L, and E? Well, if you look at this, you could say that E times L squared will change the exponent here to be 1. And you'll say that, well, E times L squared gives me P. So the problem is you cannot make a pi group if your grouping includes 3 different guys. And the procedure you do when that happens, you say, well, I can't do it with 3 guys, so the best I could do is I could say that my grouping is going to have to be lowered. And here we say just subtract 1 and then try again. And if we ignore del, we could try these combinations, LE, PL, and PE, and try to find a grouping among those guys. Now, if we immediately look at L and E, well, we know that L doesn't have mass or time, so automatically you can't make a pi group of it, because you can't write L as a combination of E, and you can't write E as a combination of L. So here we're good. You just solve the rest of the problem the way we solve the other 2, except you'd use the grouping here. Now, also note that the grouping you choose is not necessarily unique. In other words, you could choose this grouping, or this grouping, and you could get a solution to the problem. So the solution that you get to the problem when you're using the Buckingham pi theorem is not always unique. Okay, let's do another sort of tricky example. So again, this time we want to write angular velocity as a function of these guys. So the first step is always going to be find out how many variables we have. And since they've already given us this, we know that we're going to have 6 variables. We're going to have 1 over here and 5 over here. Next thing, as usual, is to write out the variables with their dimensional representations. Okay, well, things get a little tricky here. Why? when you think about n, which is defined to be the number of blades, that's already dimensionless, because just having, say, 5 of something doesn't have any dimension. Same thing over here, we're given the ratio of 2 lengths. So that's already dimensionless as well, because it would be length over length, which just gets you 1. So that doesn't have any dimension. Regardless, we still have 3 different dimensions going on here. We have mass, length, and time, so our j is still greater than or equal to 3. Sorry, our j is less than or equal to 3. Okay, so then remember, what are we interested in doing? We're trying to get a pi group that contains omega to be a function of 2 other pi groups. Remember, pi groups are dimensionless. Well, we already have 2 dimensionless groups, don't we? Because these guys are already dimensionless. And remember, our Buckingham pi theorem said we're going to have n minus j pi groups, and that's going to be 6 minus 3. So 2 of our pi groups are already taken care of, because these are actually dimensionless groups in disguise. So let's put that down. H over L is already a pi group, and n is already a pi group because both of them are already dimensionless. Also, check out over here, a lot of people mess this up. Your angular velocity only is going to be in the units of inverse time. You might get confused and say, well, it's radians per second or revolutions per second, but just know that the angle there is not an actual dimension. I think I'll talk about that again in the next problem, so try not to freak out about it too much right now. Sorry, I'm flipping through a bunch of windows. Okay, so again, the only pi group we have left to find is the one with our angular velocity. So with the last 3 problems, we're going to use the same procedure. We're going to say the variable that we're interested in times a product of our repeating variables raised to exponents. Well, how did I choose these repeating variables? Well, remember, this guy is already a pi group. This guy is already a pi group. This guy over here is the guy we're interested in. Remember, our repeating group needs to have j guys, or 3 guys. Well, the only guys that are left are these 3 over here. So that's how I chose these guys as our repeating group. Then once again, you take the dimensional representations, you put that in the equation, you solve the system of linear equations for the exponents. Once you have the exponents, you can write out what the pi group looks like. That's going to be this. We have that 0, so this guy's actually just going to fade away to 1. And remember, we already found the other 2 pi groups because they are just already dimensionless. So the Buckingham pi theorem says this right over here, pi 1, which has a angular velocity in it, is going to be a function of the other 2 pi groups. So it says that we could say this. That's all there is there. All right, let's do one last problem. Okay, so the first thing is that the only thing we've cared about so far is basically the function we're trying to get. So I'm going to tell you that's also the case here, and this picture here is completely useless to you. So I'm going to get rid of it. Okay, so this time we have a torque, and we're saying the torque depends upon the radius r, angular velocity, fluid viscosity, and cone angle. So this time they didn't write out the actual function for you, but you should know by doing enough of these problems that what you're looking for is the torque as a function of the other 4 variables. So again, we have 4 over here and 1 over here, so our total number of variables is going to be 5. The next thing you're going to do is you're going to take each variable and get the dimensional representation, and that's going to look like this. Now once again, I was saying earlier that angular velocity is usually radians per second. Well, over here, notice that the angle, the cone angle we're talking about, doesn't have a dimension. Okay, again, why is that? Well, when you're talking about certain things such as mg cosine theta for the force of something going along an incline, well, think about what you're really saying there. The dimensions are still going to be in newtons, right? So they're going to be in mg. This cosine theta here doesn't actually have a unit, because you're just going to get some sort of constant multiplier, and it's not going to affect the dimensions of your problem. So that's what we mean, or that's what I mean when I'm saying that theta can't be a dimension. We don't have a radians or anything when we're doing the Buckingham pi theorem. So here we have n equals 5. We're saying j is going to be less than or equal to 3 if nothing weird happens. So we know that we're going to have n minus j pi groups. Well, just like we were saying before, since that theta can't have a degrees is a dimension, we already know that theta is going to be one of the pi groups. So the only other pi group is going to be, well, let's see. Remember, our repeated grouping must have 3 guys. This is already a pi group. Didn't really mean to make that orange, but sure, let's go with it. We know that the variable we're interested in is going to be this m. Remember, that's going to be torque. So our repeated grouping is going to consist of these 3 other guys, because they're the only ones that's left. So let's write that out. So that will get us this. Remember, the guy we're interested in times the other guys, also known as the repeated grouping, with the exponents up there. You take the dimensional representation for each of these, you sub that into this equation, and you say that, again, I should say that this is a 1, so I'm just going to get rid of it over here. We say that their exponents must add up to 0 to remain dimensionless. So if you solve that system, you get the exponents, you slam those up there, and you get your pi group. So in this case, your pi group for the torque is going to be this, and that just comes from these exponents. You can do the algebra if you want. I find it not very interesting in regards to the actual problem. And again, from the Buckingham pi theorem, what we're really saying is that a pi group can be expressed as a function of the other pi groups. And here, since n minus j equals 2, we're really saying that the first pi group can be expressed as a function of the other pi group. Remember, the other pi group was simply theta, or the cone angle that we were talking about earlier. We're told an additional piece of information. We're told that the torque is directly proportional to theta. So this tells us the actual relationship between these 2 pi groups. Remember, if it's directly proportional to something, then it's saying one thing is going to be some constant times the other to the first power. Now, if it said there was a quadratic relationship here, then you'd have one pi group is proportional to a constant times the other pi group squared. So your final representation is simply going to be this. I know that was a little bit confusing. I'd like to go into the theory a little bit more, but I find that most engineers don't have the linear algebra experience to actually understand arguments such as rank and nullity in vector spaces. So I'm just going to go with, hopefully the examples will show you enough of how this works, and I think I've covered the tricky parts. So on that note, I'll see you guys next time. And the reason, well, actually, I'll talk about the reason why we care about this in the